Hello everyone. Today we're going to look at an extremely important type of series called power series. In a nutshell, a power series is basically a never-ending polynomial, or a polynomial with infinite degree. You keep on adding higher and higher order terms forever, and if you stop at the nth term, you get an n-degree polynomial. All of the following are examples of power series. A power series is any series of the form sigma sum c sub n times x to the power n, where the c sub n can be any real numbers, and we call them coefficients. I guess you could say this formula sums up all the examples of power series. Sorry, I'll stop. Actually, power series can look a little different than what I've shown. They can be what we call centered at different points. What I've shown so far are power series centered at 0, but you can center them about any real number you want by doing a translation to the variable x. So all of the following are also power series, just centered at different numbers, which we'll call a. Okay, well, one of the main things we always want to know about any series is, does it converge or does it diverge? Well, in the case of power series, the answer depends on the value of x. Plugging in different values of x will give you different series, some of which converge and others which diverge. I guess in a sense you could say a power series isn't truly a standalone series. Rather, it is a template for a series, and you obtain an actual concrete series once you plug in a value for x. So what values of x give us convergent series, and what values don't? Well, for starters, it's pretty clear that any power series has to converge at its center point. If I plug in a for the value of x, all of the terms of the series become 0, except the initial term. But what about other values of x besides the center point? It turns out that for any power series, the set of x values for which it converges is always an interval centered at the power series center point a. This interval is called the interval of convergence of the power series. Since the interval of convergence is always centered at the number a, we call the distance between a and either endpoint of the interval the radius of convergence, and denote it with the letter r. Thus, the endpoints of any power series are a minus r and a plus r. The exact value of r is determined by the coefficient c sub n of your power series. Change the coefficients, and you change the radius. In fact, it turns out the radius can even be infinite or 0, again depending on the exact values of the coefficients. R equals infinity means the interval of convergence is the entire real number line, from negative infinity to positive infinity. R equals 0 means the interval of convergence only contains one single point, the center point a, at which any power series always converges. But for the most part, we'll be looking at series whose radius is both positive and finite. Alright, but how do we actually compute the radius of convergence? We know it depends on the coefficient c sub n, but how do we derive the exact value of the radius from them? The answer is the ratio test. It turns out the ratio test works very, very well on power series, which would make some sense because, if you remember what I said last video, the ratio test tends to work well on series whose terms involve exponentials and factorials. And since power series always contain a factor raised to the power n, the ratio test looks very inviting. Actually, there's one important point I need to make clear about the interval of convergence before going on. I've been representing the interval of convergence so far as an open interval from a minus r to a plus r, but really, the endpoints of the interval of convergence don't have to be open. They could be closed, or even half open or half closed. Again, it all depends on the coefficient c sub n. The ratio test gives us a way to find what the endpoints of the interval of convergence are, but it cannot tell us whether a given endpoint should be included as part of the interval or not. To decide that, we have to use a test other than the ratio test. Alright, so let's try to find the radius and interval of convergence of a few power series. Alright, so let's start off with this one. So sigma sum from n equals 0 to infinity of 5 to the n times x to the n divided by n factorial. Alright, so as a reminder, what we're trying to do is we are trying to find the interval of x values such that if I plug in any of those values in for this x, I will get a convergent series. And so the main tool we'll be using to do that is the ratio test. So what does the ratio test say? So it says I need to take the ratio of the next term divided by the current term, and take the limit of that in absolute value and see what I get. If what I get is less than 1, it converges. If it's greater than 1, it diverges. And if it's equal to 1, then we still don't know. All right, so let's see what this looks like. So take the absolute value of a sub n plus 1 over a sub n. So I'm going to write my n plus 1 first. So that's going to be 5 to the n plus 1. Every copy of n becomes n plus 1. X to the n plus 1 divided by n plus 1 factorial. All right, and so next I need to divide by a sub n. But instead of dividing a fraction by another fraction, I'm just going to multiply by the original a sub n, which is this thing, but it's reciprocal. So that'll just be n factorial divided by 5 to the n times x to the n. All right, so let's clean that up a little bit. A lot of stuff ought to cancel. That's the hope anyway, if the ratio test is actually a good idea. All right, so I think yes. So so over here we have n copies of 5, and here we have n copies of 5 plus 1 extra. So almost all of these are going to cancel. We have x to the n copies of x and n copies of x and an extra 1 over there. So this one cancels with all but one of the x's. All right, so I think we're just going to have left, so far anyway, 5 times x times n factorial divided by n plus 1 factorial. And if you remember from last time, there's a way to do a cancellation with this as well, if you remember what the definition of factorial is. So what I'm going to do is let me go and write out what the definition of n plus 1 factorial is. So that's n plus 1 times n minus 1, all the way down to 2, and then times 1, all the way down to 1. But here is the idea. This piece of the entire factorial expression, n times n minus 1 all the way down to 2 times 1, well, that's just the definition of n factorial. N plus 1 factorial is just n factorial, except you tacked on an additional factor at the end. So in that case, this is going to cancel with all of these. And so what we're left with is going to be absolute value of 5x over just n plus 1. All right, so that's quite a bit of a simplification. So what about the absolute value bars? Can I drop those? Almost. So n plus 1 is always positive, 5 is always positive, but x could be positive or negative. But I can clean it up a little bit. Let me just, since everything else except x is already guaranteed to be positive, I don't need to take the absolute value of anything except just the x. So I'm just going to write this as 5 times absolute value of x over n plus 1. All right, so now it's time to take the limit. And so remember what we're doing here. It's easy to mix this up if you're doing this the first few times. Remember what we're taking the limit of is n, so not x. So x should be treated as if it's a constant in this case. It's like pi or e or something like that. Don't think of it as a variable in the context of applying the ratio test. So we're taking n to infinity. So if I'm taking n to infinity and leaving x just being a fixed number, well, then the denominator gets huge, the numerator stays constant, so this thing is going to converge to 0 as n goes to infinity. And of course 0 is definitely less than 1, and so by the ratio test, this converges. Okay, so what have we just shown then? So ratio test says this converges. What converges? What exactly? Well, this series that we started with. And kind of the interesting thing about this example anyway is it doesn't matter what x is. You notice that as n goes to infinity, and again, if you just keep x fixed as a constant, no matter what x is, If n goes to infinity, it's going to overwhelm x eventually and going to give you 0, and the ratio test will tell you it converges. So in this case, this series converges regardless of x. Any x value will work as long as you keep it fixed and you don't vary it as n varies. So in that case, that tells us that the interval of convergence is all real numbers. It is minus infinity to infinity, which of course means that the radius of convergence has to be infinite as well. All right, so that's one example for you guys. So let's look at another one then. So sigma sum n equals 1 to infinity of x to the n divided by n times negative 6 to the n. All right, so again, we're looking to find the interval of x values such that if we plug in any x value in that interval, we get a convergent series over here. So again, the tool is the ratio test. Ratio of a sub n plus 1 over, a sub n in absolute value. So in this case, so step 1, copy this formula, except replace every copy of n with n plus 1. So I think we get that. And then multiply by the reciprocal of the original. That's the same as dividing by the original. So n times negative 6 to the power n divided by x to the n. All right, so hopefully a lot of stuff should cancel, and I think it does. X to the n cancels with all but one copy of the n plus 1 copies of x upstairs. And similar thing happens here, except kind of the other way around. N copies of negative 6, n copies of negative 6 plus 1. So all but one copy cancels. This time the surviving factor is the one down below. And n and n plus 1, those don't cancel or anything as is, so we'll just leave them. So I think what we're left with is x times n divided by n plus 1 times negative 6. All right, so let me go and simplify the absolute values a little bit. So we have a negative 6 down below, so after I take the absolute value, it will become positive. All of the other factors are positive except possibly the x. So in that case, the only thing I need to enclose in absolute values is just the x. And I'll replace the negative 6 with a positive 6. All right, so now we want to take the limit as n goes to infinity. And again, remember, the emphasis is on n in this case. We're not taking x to infinity. We shouldn't be thinking of x as a variable in this case. We should be thinking of x like a constant. So if x is a constant, then as far as the variable n is concerned, what we've got here is a rational function, polynomial over polynomial. Absolute value of x is just a weird-looking coefficient for n. So if I let me go and distribute through the denominator one more step real quick to maybe make this very clear. I get 6n plus 1. And so what we have then is, as far as the variable n is concerned, we have a rational function. We have polynomial over polynomial. The top is a linear function in n. It just happens to have the weird-looking coefficient absolute value of x. And down below, it's also linear with coefficient 6. And since the top and bottom have the same degree, if we take the limit, again, as n, not x, goes to infinity, we just take the ratio of the coefficients, or the leading coefficients. So that will be, I think, absolute value of x is the leading coefficient on top, and 6 is the leading coefficient on bottom. All right, so we get this, and so the question then is, so according to the ratio test, we get convergence, indeed absolute convergence, if this thing is less than 1. So this is the thing that we want. And so now now ratio test business is done. Now we're going to actually try to hunt for the x value, because in this case, unlike the previous case, we didn't get a constant which we could tell immediately, oh yeah, we got 0, definitely less than 1, we're done. In this case, we have this expression is less than 1. So is this expression less than 1? Well, it depends on what x is. So now we're going to go back to thinking of x as a variable. So if I plug in a small value of x, yes, we get this happening. If I plug in a big value of x, then it doesn't work. So what we're going to do then is, if we want to find which x values cause this inequality to be satisfied and hence pass the ratio test, I need to solve this inequality for x. All right, well, the game of solving inequalities is very similar to equations. We just need to isolate x. So first step along the way is probably to go and move the denominator over to the other side. So I'm going to get absolute value of x is strictly less than 6. And now I need to undo the absolute value. So it turns out, in the case of an inequality like this, if you have a less than, this doesn't work if this says greater than, but if you have less than, you can actually break apart this inequality into two inequalities and get rid of the absolute value. So this breaks apart into -6 less than x less than +6. Which should make sense, right? So what this is saying is the magnitude, that is the size of x, the number x, whatever it is, the size of x is less than 6. So what numbers in magnitude are smaller than 6? Well, anything from -6 up to 6. All right, and so the upshot is we got rid of the absolute value. And indeed, I think we're basically done here. We know that x needs to be between -6 and 6. That translates into an interval. The interval from -6 to 6. And what's the radius then? So the radius of an interval like this, so the radius is just going to be half the length. Well, the length of this interval, the interval from -6 up to 6, that has length 12 divided by 2, and we get that the radius has to be 6. Although we're actually not quite done. We're very close. So r equals 6, we've got that, but this interval may or may not actually be correct. So what's the issue here? So remember, what we're doing is, in applying the ratio test, we're setting this thing to be less than 1, because that's the condition in which we know convergence. But remember that the ratio test is inconclusive if it equals 1. And this thing equaling 1 corresponds to the two endpoints, -6 and 6. If you change this less than sign into an equal sign, then solving this becomes x equals ±6. And so what that means is -6 and 6, ratio test doesn't know. So these two endpoints are unknown at the moment. Everything in between them is definitely known to be convergent by the ratio test, but the endpoints are not known. So really what we've shown so far is that the interval of convergence is at least this open interval. But it's possible that the two endpoints might be included, or maybe only one of them is included. We still don't know. So how do we find out? Well, not with the ratio test. So what we need to do is take each of these endpoints independently, plug it in for x, and see what series we get, and try to decide the convergence of that series, again, without using the ratio test, because we'd just be going around in circles then. All right, so we have to test each of them in turn. So let me start with, I guess, the leftmost one. So I'm going to test x equals -6. Let's test this boundary point. All right, so if I plug in x equals -6, what does my series become, the original series up here? I'm going to get sigma sum of, I think, -6 to the n divided by n times -6 to the n. Oh, well, that's rather convenient. In that case, both copies of -6 to the n cancel out completely, and so we're just left with 1 on top divided by n. And I think we know the convergence status of this. This is divergent. So, all right, so I plug in x equals -6, and I get a divergent series. So therefore, -6 definitely should not be part of the interval of convergence. So in that case, -6 should have a parenthesis as it does. So nothing needs to change here. All right. All right, so now let's test the other endpoint. So let's test x equals +6. Plug it in. So if I plug in positive 6, I'm going to wind up having 6 to the n on top and n times negative 6 to the n on bottom. And this looks quite a bit like there should be some cancellation again, but not quite. So I think I'm going to, in order to see how it cancels, I'm going to do this. So let me go and, in a sense, factor out the negative from this negative 6. So I'm going to get 6 to the n divided by n times negative 1 to the power n times, oops, I just factored out the negative, should not be there, times 6 to the n. Well, okay, I guess I don't need the parentheses. Ugh. Sorry about that. Times 6 to the n. All right, so now the 6 to the n's definitely cancel out. And so what are we left with? We're left with, I think, 1 divided by n times negative 1 to the n. So this negative 1 to the n, it's just multiplying the n. It's just causing the series to alternate between plus or minus, plus or minus, plus or minus. And so this then is an alternating series, and so we should be able to decide whether it converges or not with the alternating series test. And so what does the alternating series test say? Well, it says that if the non-alternating version, that is just 1 over n, if the terms of the series, so let me take that out real quick. So the non-alternating version of the terms, 1 over n, if that thing goes to 0, then we're guaranteed to have convergence in this case. And indeed, 1 over n does go to 0, again, as a sequence of terms. I'm not thinking about this as a series at the moment. 1 over n goes to 0 as a sequence of terms. And because this is in the context of an alternating series, that is enough to conclude convergence. If you're alternating, terms are decreasing, and they decrease to 0, then you converge. That is the alternating series test. All right, so I plugged in 6, and I wound up getting, actually, a convergent series. So what that means is 6 should actually be included as part of the interval of convergence. So in that case, I will represent that by getting rid of that parenthesis and replacing it with a bracket. And that, then, is the full story. That is the full interval of convergence. All right, so not bad, not bad. So the process may seem a bit involved right now, but that's because we're just starting out. I think you will start to be able to speed this up quite a bit as you get more practice at it, so don't be too concerned. All right, so to help with that, let's go on to another example. All right, so let's find the interval and radius of convergence of this series, sigma sum n equals 1 to infinity, of 3n times x minus 2 to the power n divided by 5 to the n minus 1. All right, well, I think we know the drill. Let's start off with the ratio test and take the ratio of a sub n plus 1 over a sub n. So what are we going to get? Every copy of n turns into an n plus 1. So this is going to be 3 times n plus 1 times x minus 2 to the power n plus 1 divided by 5 to the n plus 1 minus 1. Well, plus 1 and minus 1 cancel, so that actually just becomes 5 to the n. All right, then we multiply by the reciprocal of the original, so that is 5 to the n minus 1 divided by 3n x minus 2 to the power n. All right, so let's cancel some stuff out. So what cancels? N plus 1 exponent here, just plain n down there, so everything except one copy cancels. 3 cancels with 3, so that's a little bit of a cleanup. And over here we have n minus 1 copies of 5, and we have n copies of 5 here, so we have 1 extra copy of 5 down here. So all of those cancel, and all but 1 cancels down here. And I think that's all that we can cancel for now. So I think that'll leave us then with n plus 1 times x minus 2 divided by 5 times n. All right, so I think all of these factors are positive, except possibly the x minus 2. So I will just condense all of the absolute values onto x minus 2 and free all the other factors from its iron grip. All right, so what we're left with is this maybe awkward-looking thing. But again, so what are we trying to do here? So we're trying to take the limit as n goes to infinity, and we're going to treat x as if it's a constant. So in that case, pretending all of this blob in absolute values is a constant, maybe it's 3 or whatever, then what we've got is, again, a rational function in terms of n. So we have a linear over a linear. And so in that case, if we want to take the limit, I need to take it's going to be the ratio of the leading coefficients. So let me find what the leading coefficients are, or at least as far as n is concerned. All right, well, to get those, let me go and distribute this thing to each copy of n. So that's going to give me x minus 2 times n plus x minus 2, all divided by 5n. And again, so remember, x minus 2 is just a stand-in for a constant in this case. So the ratio of my leading coefficients is going to be x minus 2 in absolute value over 5. All right, and according to the ratio test, we are looking to make this ratio. We want this ratio to be less than 1. All right, so we're hunting for x values that make this true. So let's solve the inequality then. So multiply both sides by 5, and we get x minus 2 is strictly less than 5. And if I want to undo the absolute value, they break apart like this. So we have negative 5 less than x minus 2 without the absolute values, less than 5. All right. So we're not quite done yet. We have x minus 2, but again, to go and isolate x, it's pretty clear what we need to do. We need to add 2 to all sides. So add 2 to all sides. And we're going to get, I think, minus 3 less than x, less than 7. X is in between minus 3 and 7. All right, so that tells me that my interval of convergence is at least the open interval from minus 3 to 7. Again, at least. We still need to check the endpoints. But regardless of the endpoints, we know what the radius needs to be. It's going to be half the length of this interval. So what is the length of this interval? Okay, so half that length. So the length is going to be 7 minus negative 3. So 7 plus 3, that's 1/2 of 10, which is 5. All right, so radius of convergence is 5. All right, so now we need to establish which, if any, endpoints need to be included as part of the interval of convergence. All right, so there's nothing to do there except just to test them one by one. So I'm going to test x equals minus 3. Plug it into the original series, and I'm going to get sigma sum n equals 1 to infinity of 3n times, and if I plug in a negative 3 there, I'm going to get negative 3 minus 2. So I think that's a minus 5 to the power n, divided by positive 5 to the power n minus 1. I think, right? All right, so similar trick. I'm pretty sure these things look like they should cancel. But in order to actually make them cancel, I need them to look exactly the same. So what I'm going to do is distribute the n to both the negative sign and the 5. And so I'm going to get 3n times negative 1 to the n times 5 to the n divided by 5 to the n minus 1. All right, so similar to before, 5 to the n minus 1 completely cancels with all but one copy of the 5 upstairs. And so what I'm going to be left with is, let's see, this series. So I have the minus 1 to the n as just going to be there, so I'll put it at the beginning. And then I have 3 times 5, so I have 15n. All right, so again, I have an alternating series. So does this one converge? Well, to answer that, I need to look at the non-alternating version of the series and just look at its terms. So that would be just 15n. And if I take 15n and take n to infinity, this is just going to diverge, it's going to blow up, right? So in that case, by the alternating series test, this thing has got to diverge. By the alternating series test, or actually the good old divergence test. If you want to forget about all of the alternating stuff, you can actually establish divergence here with just the good old divergence test. You take n to infinity, the terms are just going to grow larger and larger. They're going to start flipping back and forth between larger and larger positive and negative numbers. Certainly isn't going to converge. So yep. So in that case, -3 definitely should stay excluded. That does not turn into a bracket. So what about 7 then? So if I plug in x equals 7, what's going to happen to my original series? Well, if I plug in 7 into the original series, 7 minus 2 is 5. So it looks like I'm going to get 3 to the n times positive 5 to the n divided by 5 to the n minus 1. Well, that looks a little bit familiar. It looks exactly like this, except we don't have the -1 to the n factor. So, all right, well, this cancels with all but one of those. And so we're left with sigma sum n equals 1 to infinity of 15n. And I think we can tell pretty quick that this series is going to diverge, right? Just by the good old divergence test. You take n to infinity, the terms are not shrinking to 0. Quite the contrary, they are inflating to infinity. So this thing is definitely diverging. By div test. All right, so in that case, 7 also makes it diverge, so we shouldn't include the 7 as part of the interval. So it looks like this smallest possible interval of convergence actually is the true interval of convergence. So -3 to 7, exclusive, is our interval of convergence. All right, so now it's time to go on to another one. And I warn you, it's one that I find a little bit interesting. I'm not crazy, I promise. Okay, so it's this series, sigma sum, n equals 0 to infinity of 2n quantity factorial times x plus 6 to the power n divided by n plus 4. All right, so what do we do? We take the ratio of a sub n plus 1 over a sub n. We're doing the ratio test. So what are we going to get in this case? So on top, I'm going to have, I think, so every copy of n becomes n plus 1. So here, be a little bit careful. So remember, we need to enclose the n in parentheses when we replace it with n plus 1. So this does not become... So this is not 2n plus 1 factorial. That's not what you're supposed to do. This is actually going to be 2 times the quantity n plus 1 factorial. So 2n does not become 2n plus 1. N just becomes n plus 1, and the 2 is on the side. So I stress that because that's a very easy mistake to make. All right, I think the rest is pretty straightforward. So I'm going to get an n plus 1 plus 4, so that's going to become an n plus 5. And now I multiply by the reciprocal of the original, so that's going to be n plus 4. I think I'll go ahead and put it in parentheses. And on bottom, just copy-paste. X plus 6 to the n. Well, I'm supposed to draw an absolute value bar there. Oh, there you go. All right, so let's simplify this then. Well, first of all, before I even do a whole lot of simplifying, I really want to clean up this ugly bit of garbage right here. So let me distribute the 2 through. So in that case, I'm going to get 2n plus 2 factorial times x plus 6 to the power n plus 1, and I'll go ahead and condense the entire fraction. So this will become times n plus 4, all in the numerator. And down below, we're going to have n plus 5 times 2n quantity factorial times x plus 6 to the n. All right, so let's see what cancels with what over here. Well, again, the exponential bits will cancel almost entirely. So this will cancel with all but one copy upstairs. N plus 4 does not cancel with n plus 5, so I think they both just have to stand. All right, what about the factorials here? So I think we encountered something like this once before. So in this case, yeah, so let me go and again write out the factors of this upper factorial, because this is the bigger one, right? So we're taking a bigger number factorial, and here's a smaller one. So presumably this one cancels completely away and leaves some leftovers on top, but let's try to see what those leftovers would be. All right, so 2n plus 2, so that is, or factorial, that is 2n plus 2 times 2n plus 1 times 2n, and then it just keeps on going from there. But I think I can stop at 2n, right? So after that, it's just going to keep on going, which is to say it's a factorial. And so what am I left with on bottom? Well, okay, let me go ahead and finish the numerator real quick. So what am I left with on the bottom then? So I have n plus 5 times 2n factorial, and I think that's it. All right, so it looks like if I write out two factors of 2n plus 2 factorial, then I see the bit that cancels with the denominator. So those two cancel. And so I'm left with absolute value of 2n plus 2 times 2n plus 1 times x plus 6 times another n factor awkwardly over on that side. And on bottom, we just have n plus 5. All right, well, all the factors are positive except possibly the x plus 6 factor. So let me condense the absolute values. I think I'm also going to rearrange the order of multiplication here, so I put the x plus 6 first. I think that makes sense because we want to think of it as being like a constant. All right, so we have this then. N plus 4, and on the bottom we have n plus 5. All right, so we're taking the limit then as n goes to infinity, right? So, and in this case, again, as a reminder, x should be thought of as a constant, so this blob should really be thought of as a constant. So in that case, let me ignore it for the moment. I have a rational function. What's its degree? Well, I have linear times linear times linear, so this is a degree 3 on top, a cubic. And on bottom, I have a degree 1, a linear. So I have a top-heavy rational function. And in that case, if I take the limit as n goes to infinity, it doesn't matter what the coefficients are. This thing is just going to blow up to infinity, no matter what coefficients I have. Well, okay, so, well, almost for any coefficient. It turns out there is actually one little exception. If it turns out that this coefficient, this constant, x plus 6, if that thing turns out to be 0, well, then that'll annihilate everything. I'll have 0 on top and n plus 5 on bottom, so it will actually converge trivially to 0. But that's the only exception. If x plus 6 is anything other than 0, this thing is going to diverge to infinity as n goes to infinity. Unless x plus 6 is equal to 0. All right, but it actually turns out this is a bit important. So if x plus 6 does equal 0, then this thing is trivially convergent. So this thing converges to 0 as n goes to infinity if that does happen. And again, we're looking for all x values that make it converge. So evidently, x values that cause this thing to be non-zero are definitely out of the picture, but x values that do cause this equation to hold true, x plus 6 in absolute value to be 0, that does lead to something convergent, because 0 is less than 1, which according to the ratio test should mean it converges. So what values of x make this thing true? Well, if the absolute value of something is equal to 0, then it must mean that whatever that something is 0. 0 has no sign, so there's no need to write an absolute value there. If this thing equals 0, then the thing inside the absolute value equals 0. So in that case, it looks like the only x value that's going to lead to a convergent series is x equals minus 6. Does that make any sense? I think so, right? So if we look at this, this is a power series which is centered at -6, right? So remember that the general form of a power series is sigma sum of c sub n times x minus a to the n. In order to get x plus 6 to show up here, I need to pick a equals -6. And I will get my x plus 6 up there. So the center of this series is at x equals -6. And as I mentioned earlier, a power series always converges at least at its center point. So indeed, this makes sense. That's what we should expect. But we've shown that it's not going to work anywhere else. For any other x values, if I plug in anything except -6, then this equation is going to break. X plus 6 in absolute value. If x is not -6, this is going to be some non-zero positive number, which means if you take n to infinity, the entire fraction is going to go to infinity, and so you get that it diverges by the ratio test. So what that means is our interval of convergence really consists of only one number. It is just -6 all by itself. So the way we write that is we enclose it in braces. So our interval, if you want to call it an interval, is just the single solitary number -6. So that is our interval of convergence. And if you just have a single point, just the center point, then your radius is just going to be 0. A single point has no width. All right, so just to summarize real quick what we just did. So we took the ratio test, and we found that if x is not equal to -6, then this ratio in the limit goes to infinity, which implies divergence. But if we plug in x equals -6, then we get that this ratio, the ratio of a sub n plus 1 over a sub n, turns out to be equal to 0, which is convergent. So therefore, by the ratio test, it converges only at x equals -6. And for any other value of x, we're going to get the ratio going to infinity, and so it's game over. Okay, so let's move on then. All right, so let's do this series. Sigma sum n equals 0 to infinity of -4 to the n times 2x minus 5 to the power n, all divided by n squared plus 5. All right, well, we know where to start. Take the ratio. All right, so I have a feeling this one might get a little bit big, so I'm going to go and write it down here. So plug in n plus 1. I'm going to get -4 to the n plus 1 times 2x minus 5 to the n plus 1, all divided by n plus 1 quantity squared plus 5. And then multiply by the reciprocal of the original, so that's going to be an n squared plus 5 on top, and -4 to the n times 2x minus 5 to the n on bottom. All right, so as usual, we have the usual cancellation of the term, or the factor with an x in it. And what else do we have going on? So it looks like, the -4 to the n plus 1 cancels almost entirely with this one, so this one cancels with all but one copy of the -4. So we have that as well, and I think that's all we can do for the moment. N squared plus 5 does not really cancel with this thing, or at least it doesn't seem like it does. All right, so what we're left with then is on top we have minus 4 times 2x minus 5 times n squared plus 5. And down below, I think we just have this. So n plus 1 squared plus 5. All right, so let's condense the absolute values a bit. So this minus 4, if I take the absolute value, it'll become a positive 4, so I can make that change. Every other factor is going to be positive, except possibly the 2x minus 5. So I think this can be simplified into 4 times the absolute value of 2x minus 5. And then everything else is normal. All right, so again, this looks a bit complicated. We're trying to take n to infinity, right? But again, so remember, we're just interested in thinking of n as the variable, and anything with an x in it is just a constant as far as we're concerned. So in this case, it looks like, again, all of this blob over here is just a coefficient. So I have a quadratic over a quadratic. So this is another rational function where the top and bottom have the same degree. So in that case, if I take the limit as n goes to infinity, it's just going to be the ratio of the leading coefficients. And I think you can tell what those are in advance, right? So what would I do? In order to get the actual leading coefficients, I would need to distribute this through. All right, well, I can pretend to do that. I'm not going to go through all of it because, again, we just care about the leading term. So I think if we were to pretend to do that, we would have 4 times 2x minus 5 times n squared, and then plus some garbage over here, which we don't care about. And downstairs, if I was to square this thing, I would have an n squared plus yada yada plus 5. So this is just going to wind up being n squared plus some change on the bottom. So in that case, my leading coefficients are going to be this entire blob with an x in it on the numerator and just 1 in the denominator. So take the limit as n goes to infinity, and you get that the limit is just going to be, well, 4 times the absolute value of 2x minus 5. And we are looking for that to be less than 1. Again, that's what the ratio test, that's when the ratio test tells us we've got convergence. All right, so let's solve this thing for x. So step 1, I think, is pretty clear to divide by 4. So divide both sides by 4, and I'm going to get 2x minus 5 is less than a fourth. All right, next step, undo the absolute values. So turn this into a triple, or well, I guess a double inequality. So we have minus a fourth is less than 2x minus 5 is less than positive a fourth. All right, then add 5 to both sides. So let's see, what is 5? I need a common denominator. So 5 can be rewritten as, I think, 20/4, right? So add that to both sides, and I'm going to have 20/4 minus a fourth, so that's a 19/4 on the left-hand side, and a 21/4 on the right-hand side. And now divide all sides by 2, and I'm going to get 19/8 is less than x is less than 21/8. All right, so now that I'm down to that point, it's pretty clear what the interval, or at least the minimum interval of convergence has to be. It's got to be at least the interval from 19/8 up to 21/8 exclusive, at least. But that's enough to tell us what the radius of convergence is. So radius is 1/2 the length of this interval. So the length of the interval is 21/8 minus 19/8. Subtract the two endpoints. So that's going to give me 1/2 of 2/8, which is just 1/8. So that be our radius of convergence, 1/8. Okay, so now to decide on the endpoints. So I need to plug each of them individually back into the original series, which is way up there. So let me go and reproduce it down here. So our original series is sigma sum n equals 0 to infinity, minus 4 to the n, 2x minus 5 to the n, divided by n squared plus 5. All right, so let's test these out. So I'm going to test x equals 19/8 to start off. So if I plug that in, what happens? Well, so I think the critical thing, if x equals 19/8, if you plug that into 2x minus 5, what you wind up getting is this is minus a fourth. All right, so in that case, my series becomes sigma sum of minus 4 to the n times negative a fourth to the n, all divided by n squared plus 5. All right, well, these two have the same exponent n, so I can actually merge their bases together. So this becomes sigma sum of negative 4 times negative 1/4, which I think is actually just 1. 1 to the power n. But 1 to the power n is always 1, no matter what n is, so I actually don't need to write that either. And I think this one we can tell converges, either with the limit comparison test or the direct comparison test. But I think direct will actually do it for us. So I can make this series larger by getting rid of the plus 5. Right? So I made the denominator smaller, series gets bigger. All right, and so that is definitely convergent. All right, so plugging in 19/8 gave us a convergent series. So in that case, 19/8 should be included in the interval of convergence. So we'll turn that into a bracket. All right, so next up, we'll test plugging in 21/8. So if I plug in 21/8, what do I get? Well, what am I going to get? I'm going to have 2x minus 5 is going to become a positive 1/4 in this case. And so what does that mean for my series? So my series is going to become sigma sum of negative 4 to the n times a positive 4 to the power n over n squared plus 5. So again, I'll do the same trick of merging the two bases because the exponents are the same, n in both cases. So negative 4 times a fourth, that is just going to be negative 1 to the n. So, okay, so this is basically what we had before, except it's an alternating version of it. But the alternating version of it is making a series alternating is not going to, or making a convergent series alternating is certainly not going to make it divergent. This is definitely still going to converge. And you can see why. If you apply the alternating series test, you take the positive version of the terms. And the positive version of the terms is this right here. And if I take n to infinity, that goes to 0. So indeed, this thing also converges by the alternating series test. So indeed, 21/8 should also be included. So in this case, both of the endpoints are included in our interval of convergence. And all right, so that covers everything. So now we know what the full interval of convergence is. It's the closed interval from 19/8 to 21/8. Okay, so I have just one more example for you guys. That is sigma sum n equals 2 to infinity of 2x plus 1 to the n divided by 7 to the n times ln of n. All right, so usual drill. This is the ratio of a sub n plus 1 over a sub n in absolute value. So what do we get in this case? So I think we're going to get this piece to start off, and then we multiply by the reciprocal of the original. So 7 to the n ln of n divided by 2x plus 1 to the power n. All right, so let's see what cancels out. So this cancels with all but one copy of that. 7 to the n cancels with all but one copy down below. And I don't think the ln's will do anything, or at least not yet. So we have left then
2x plus 1 on top, ln of n, and on bottom we have 7 times ln of n plus 1. All right, so contrary to what some of you might be tempted to do here, we actually can't really condense these into a single log using the log rules. What you're thinking of is, or what you might be thinking of is if we had, say, ln of n minus ln of n plus 1, then we could turn that into ln of n divided by n plus 1. But here, if you're dividing two logs, you can't really condense that into anything nicer. So it just has to stand. All right, well, that's okay. So let's see here. Let's see if I can simplify the absolute values anyway. So I think both ln of n and certainly ln of n plus 1 are going to be positive because we're starting at n equals 2. So in that case, I can just turn this into absolute value of 2x plus 1 times ln of n divided by 7 times ln of n plus 1. Okay, so now I need to take n to infinity, and again, I pretend that the x is a constant. So take n to infinity here, so it's not really clear what's going to happen, right? We're going to have, I think, that situation of indeterminate form, infinity over infinity, although, so probably what we need to do here is to do a L'Hopital's rule. But before even doing that, I think, let's see if we can make a guess as to what this limit should be. So ln is a slow-growing function, so in that case, the difference between ln of n and ln of n plus 1 is going to be pretty minuscule for large values of n, coupled with the fact that ln is such a slow-growing function. So I'm guessing that these two in the limit are basically going to cancel out, that the limit of these two ln's in ratio is going to go to 1. But let's verify that using L'Hopital's rule. So what I think I'm going to do is break this apart into two pieces. So I'll put the absolute value and the 7 on one side, and I will put the ln stuff on another side. And now let's just focus on taking the limit of this thing. So take the limit, n goes to infinity of this. Well, as I said before, this is going to lead you to an indeterminate form of infinity over infinity. So L'Hopital's rule says you can take derivative of numerator and denominator and take the limit of that instead. So if I do that, I'm going to have 1 over n on top, and I think 1 over n plus 1 on bottom. So if I rearrange that a little bit, I think what you're going to get is, this is the limit of n plus 1 divided by n. And indeed, that one, as n goes to infinity, that's going to give you a limit of 1. So yep, as expected, this thing goes to 1. So if this thing goes to 1, then this is the only, then the factor that's next to it is the only thing that survives. So we just have 2x plus 1 divided by 7, and we want that to be less than 1, according to the ratio test. All right, so let's solve this thing for x then. So I guess I'll reproduce it down here, just so the page doesn't look too confusing. So multiply both sides by 7. And we can get rid of the absolute values by writing the inequality like this. Okay, and then subtract 1 from all sides, and divide by 2 all sides. All right, there we go. So evidently, our minimum interval of convergence has got to be the open interval from -4 to 3 at least. Again, still have to check the endpoints. So what's the radius going to be? So radius is going to be the length of this thing divided by 2. I think the length of this interval from -4 to 3, that's 7. So 7 divided by 2 is going to be my radius. All right, so now for the endpoints. All right, so I'll check the leftmost one first, because why not? So if I try x equals minus 4, what's going to happen? Well, so I guess we have to look at what the original series is. I guess I should reproduce that as well. All right, so original series was as follows. All right, so if I plug in minus 4, I'm going to get a negative, I think I'm going to get a negative 8 plus 1, so that's going to give me a minus 7. So I'm going to have minus 7 to the power n divided by 7 to the n, ln of n. All right, and so I think this should simplify by a fair amount if I factor out the minus 1 that's in there. So we have minus 1 to the n times 7 to the n divided by 7 to the n ln of n, and the 7 to the n's will cancel out. And so we're left with this alternating series. So does this thing converge or not? Well, okay, so according to the alternating series test, what I need to do is I consider the non-alternating version of the terms. So 1 over ln of n. And then I ask, what does this thing go to as n goes to infinity? Well, the denominator is going to grow to infinity very slowly, but it will. So I have 1 divided by infinity, so that is 0. And if the terms go to 0, then according to the alternating series test, we have convergence. All right, so evidently minus 4 should be part of the interval of convergence. All right, so now for the other endpoint. So that is x equals 3. So if I plug that in, what am I going to get? I think I'm going to get 2 times 3, 6 plus 1, so that's just a positive 7. So 7 to the n divided by 7 to the n, ln of n. So in that case, they're just going to cancel completely away. And so what I'm left with is just 1 divided by ln of n. Not alternating. So does this thing converge or not? Well, divergence test doesn't tell me if it diverges, right? Because if I take n to infinity, I get the limit of the terms is 0. But since this is not an alternating series, that tells me nothing. So can't do that. However, I'm inclined to think that this diverges, and here is the reason why. We know 1 over n diverges, right? If we have sigma sum of 1 over n, that diverges. In place of n in the 1 over n, I have ln of n, and ln of n is a slower growing function by far. ln of n grows way slower than just plain vanilla n. And so that makes me think then, so what that means then is that the denominator is, on the whole, going to be smaller than 1 over n. So a smaller denominator, a bigger fraction. So in that case, by the direct comparison test, I say that this thing should be bigger than the series, the harmonic series, so 1 over n. ln of n is generally smaller than n, smaller denominator, larger fraction, larger series. And this thing we know diverges. All right, so that's us using the direct comparison test. So evidently, x equals 3 is going to make a divergent series, so it should correctly be excluded from the interval of convergence. All right, so we are done then. All right, so now we're going to shift gears a little bit and do a couple of examples in a more analytical vein. So what we've been doing so far is kind of computation-based, trying to find the interval of convergence or the radius of convergence. So now I want to do something that is a little more, I guess, implicit, or kind of needs some more analysis. It's not just something where you're rolling through it like a machine. So it kind of depends on, again, the fundamental properties that we've established about power series, which is the interval of convergence is always centered at the, well, center point of the series, and it always has a certain radius. So it turns out just that fact by itself gives us enough to learn some interesting results here. So let's start off with this example. Suppose we have some series, we don't know what its coefficients are. We know it's centered at 0, but we don't know what its coefficients are. So we have some sort of power series, and somehow we know that it converges if x equals 4. So if you plug in 4 in for x, you get a convergent series. But if you go and plug in x equals -7, you wind up getting a divergent series. So the question is, just based on that bit of information alone, what can we say about the convergence or divergence of the following series? And so the first one that I want to look at is this one. So sigma sum n equals 0 to infinity of c sub n times 8 to the n. All right, so if we look at this for a moment, it looks a lot like the original series we started with. We have the same coefficient sequence, c sub n, but the only thing is x has been replaced with an 8. So, all right, so this is our original power series where x equals 8. So really what we're asking here is, so we're asking whether does this thing converge or diverge. That is the same thing as asking, in this case, is 8 in the interval of convergence or not? So, well, we don't know what the interval of convergence is, not exactly, but I think we can learn a little bit about it. At any rate, what can we say about the radius of convergence in this case? So we know that the series converges if x equals 4 and it diverges for x equals -7. So let me go and kind of draw a number line real quick and record what that really tells us. All right, so here's our number line, and there is 0, which also happens to be the center point in this case. So what do we know? We know that at x equals 4, over here, it's going to be convergent. Here's -4. And over here at -7, it is going to diverge. All right, so think about what that means. Let's start off with the first bit of information we have, that it converges if x equals 4. So remember, the interval of convergence always is centered at the center point, 0 in this case, and it has some sort of radius r. Well, if we know that x is in the interval of convergence, then what that must mean is that the radius needs to be at least as big as 4. It certainly can't be any smaller than that, right? If the radius was any smaller, then even in the best case where we have a closed interval, it's going to exclude 4. But 4 is supposed to be convergent. So in that case, our minimum radius of convergence has to be 4. In some sense, you could say that given the information that this series converges at 4, the minimum possible radius of convergence has to look like this. It's closed at 4 and open at -4. And again, let me emphasize, I'm not saying this definitely is the interval of convergence. I'm saying this is the smallest possible one. This is sort of the worst case interval of convergence. It's got to at least look like that. It might be bigger, but it's got to be at least that. And so what that means then is everything inside the interval from -4 to 4, half open, half closed, has got to be convergent. So let me go and maybe illustrate that real quick. So everything in there has to converge. There might be more stuff that converges outside, but at least that converges. All right, well now, what about the other piece of information we have? We know that at -7, it definitely diverges. And so what that means is -7 has to be outside the interval of convergence, which means anything that is farther away from -7, that is further to the left of -7, or by symmetry, further to the right of +7, has definitely got to be divergent as well. None of this stuff can possibly be convergent. Why? Because if anything out here was convergent, then anything closer to the center point would also have to converge, because again, the interval is centered, or the interval is centered at 0. So the basic principle at work here is if you're convergent at one point, then all points closer to the center are also convergent. And if you are divergent at a point, then all points further away from that point, or further away from the center point, also have to diverge. So that also includes then the point in question in this case. So x equals 8, that lines up over here. That is a point that is further away from 0, the center point, than -7 is. And since -7 is already divergent, that means 8 also must diverge. So without even knowing anything else about the coefficients of the series, we know this series has to diverge. All right, so that's the basic principle. If you're closer to 0 than a convergent point, you are convergent. If you're further away, from 0 than a divergent point, then you're also divergent. So what this means then is, as far as the radius of convergence goes, so we know it has to be at least as big as 4, but it certainly isn't going to be any bigger than 7. This thing cannot be bigger than 7. So again, we still don't know what the actual radius of convergence is, but we have established this one fact about it. Whatever the radius of convergence is, it has to be between 4 and 7. So again, what I've written here is not the interval of convergence. This looks like an interval, but this is an interval of possible r values. We know r has to lie somewhere in this region right here. This is the region where r can be. It can't be any closer than 4, and it can't be any further away than 7. All right, so let's tuck that away and see if we can see what we can say about some other series. So how about this one? Sigma sum n equals 0 to infinity of c sub n times -6 to the power n. All right, well, again, this resembles our original series quite a bit. The only difference is, well, we've substituted x for we've substituted -6 for x. So in that case, this is the same as asking, is -6 in the interval of convergence? Whatever it is, it's still unknown. Well, okay, so let's think about this. So where does -6 live? So -6 is about right there, let's say. And what do we know about the radius of convergence? We know that the radius is somewhere between or possibly equal to 4 and 7. So what can we say then? Does this thing converge or not? And so if you're not sure, take a moment to try to answer that yourselves real quick. All right, so how about this? So what we did before, right, is I established kind of a minimum interval of convergence based on the fact that our series has to converge at 4. That was this highlighted yellow region right here. This interval, open here, closed there, is sort of the smallest that the interval of convergence could be. Well, what's the biggest it could possibly be? Because that information we should be able to establish from this divergence piece of information. So we know that it diverges at -7. So that means the biggest the interval of convergence could possibly be would have to be an interval whereby -7 has a parenthesis. It's excluded there. And at +7, well, we don't know. It could actually, I suppose, converge there. We don't know. So in this case, the interval from -7 up to 7, where you exclude -7, but you include +7, that is the largest our interval of convergence could be. It can't be any larger than that, and it can't be any smaller than this one. But it could be anything in between. We don't have any other information that would tell us where it falls in between here. The real, actual interval of convergence might be this one, it might be that one, it might be something in between. And depending on which one it is, changes whether -6 is inside or outside it. Like take the minimum one. If this yellow one, this yellow interval that I've written here, is the true interval of convergence, which, as far as we know, it might be, then -6 is outside of it, and so we would say, this must diverge. But if it turns out, no, this is not the actual interval of convergence, it's the biggest one, that one happens to be the actual interval of convergence, well, now it includes -6, so then we would conclude convergence. So the answer here, in this case, is it's inconclusive. We just don't have enough information to decide. -6 happens to fall within the range of possible R values, and so we don't know. All right, well, that one's a bit of a bummer. How about this one, though? This one looks maybe a bit stranger than ones you've seen before. So what about sigma sum of just C sub n? Well, how does that relate to what we started with? So what we started with was C sub n times x to the n. Is there something we can plug in for x that will generate this series? Yeah, so I think the answer is yeah, right? So if I plug in 1 in for x, then this factor just becomes a 1, and you might as well not write it. So we get sigma sum of C sub n. So this corresponds to plugging in x equals 1. All right, so is x equals 1 in any of the possible intervals of convergence? So again, we don't know what the interval of convergence is, but we have a range of possibilities. So is x equals 1 in any of them, or in all of them, or out of all of them? Well, so where does 1 lie? So 1 lies right here, right inside the yellow region. And so remember, the yellow region is the minimum, the smallest possible interval of convergence we can possibly get. So in that case, it's going to be inside all of the different possibilities. So in that case, no matter what the interval of convergence is, because this yellow one is the smallest one, it's got to converge. Doesn't matter what it is, what the actual interval of convergence is. Whatever it is, it's got to be in there. So this one definitely is convergent. All right, so one more for you. Sigma sum n equals 0 to infinity of -1 to the n times C sub n times 4 to the n. All right, so maybe let me go and reproduce the actual series we started with over here so I don't have to keep scrolling. All right. All right, so this one looks quite a bit different from that one. Is there any way to go and plug in an x value, or plug in a value for x here and get this series popping out? Kind of hard to say, maybe, but let me clean this up a little bit and it might be a bit clearer. So this one has just one single base to the power n. This one has two things to the power n. So how about we condense them? So I'll move them. So I'll combine the -1 and the 4, and that'll give me a -4 to the power n. I think you can see it now. We get this series if we plug in x equals -4 in for x. All right, so is -4 in or out? Well, -4 is right here. It's right at kind of the boundary of this yellow region, but it's actually at a parenthesis point. So it is actually outside of the minimum interval of convergence. So in that case, does that mean that this thing diverges then? Well, not necessarily. So all that I'm saying here by -4 being outside of this, technically just barely outside of this yellow interval, all that means is -4 is outside the minimum interval of convergence. It doesn't necessarily mean it's outside of whatever it actually is, because it's still unknown. Well, in that case, so is -4 inside any of the possible intervals of convergence we've got? Like maybe let's take the worst case, the maximum one. The biggest interval of convergence we have is this -7 to 7. Is -4 inside that one? Yes, it is. So in that case, I think we're inconclusive again. -4 is outside the smallest interval, but it's inside the greatest one. So in that case, it really just depends on exactly where these boundary lines fall, and so we don't actually know. So this one is, once again, inconclusive. Okay, so I have one last example for you guys. And that is this one. So example 3. Let's suppose that we're not currently watching a math video. No, I'm just kidding. Suppose the series sigma sum c sub n times x minus 2 to the power n. Let's say that we somehow magically know that this series converges if x equals 5. So in that case, the question is, on what interval can we guarantee convergence? So to be clear, what I'm asking here is not what is the interval of convergence. There's no way to establish exactly what it is unless we actually know what the c sub n's are. But what we're asking instead is on what interval can we, what's the biggest interval on which we can be sure, whatever is the interval of convergence, it definitely will converge if you're in this range. Or to put it another way, kind of similar to the last problem, we're looking for what is the smallest possible interval of convergence. What is the tightest possible interval of convergence that meets this condition that we've established here? Well, okay, so again, I think a picture is helpful here, so let me sketch a quick little number line. So I'm going to let that point be the center point. So where's the center point this time? So I think the center point's 2, right? So it's x minus a is your center point, so a is the center. So this series is centered at 2, and its interval of convergence is going to be some radius away from 2. All right, well, the piece of information we know is that at x equals 5, it converges. So we have that this is a convergent point. We don't know if anything outside of it converges, but we definitely know that stuff inside of it converges, because if x equals 5 is in the interval of convergence, that means that our radius of convergence has to be at least as big as 3. So, I mean, it might be bigger, but it has to be at least that. It has to be at least 3 in order to include x equals 5. All right, well, this is a radius, so it extends in both directions. So that does not look the same length at all. Let me try again. All right, so it also has to equally extend out to the left, which will take us all the way -3 to -1. And again, depending, it might be larger, but it has to be at least this big. So everything in this region right here has got to be convergent. The radius is at least 3. This is all of the stuff that falls within a radius of 3 of the number 2. What about the endpoints, though? Well, we already know one of the endpoints for 5. Definitely at minimum, so our minimum interval of convergence has got to at least be this yellow region, but we can actually do a little bit better than that. We, of course, know it has to include 5. It just told us here. So certainly a bracket there. But the nature of it is, of intervals of convergence in power series, is we don't know whether this one does too. So this one may not actually converge, right? So in other words, what I'm trying to say here is, if in the worst possible case the radius is actually equal to 3, then the most we can hope to say in this worst case scenario is that 5 is included because they told us so. But we don't know if -1 is, because again, at the actual value of the radius, the point is ambiguous unless you have some external information to tell you. So we don't know if -1 is included or not, so we can't guarantee it, so we should exclude it from our minimum interval. So in that case, I think we have what we were looking for. The minimum possible interval of convergence that satisfies this condition is the interval from -1 to 5, where you exclude -1, but you include +5. So again, that is not necessarily the interval of convergence. It could be, but it is the smallest possible one. I feel like I should put some joke here about Captain America and patience, but I'm not sure I can pull it off.